Welcome to Lesson 1.2, Precision, Accuracy, and Errors, the second video in a series where I teach you all of grade 11 physics. In this lesson, we'll be going over precision, accuracy, systematic and random errors, as well as how to quantify these two kinds of errors with the terms percent error and percent difference in order to understand errors numerically. Firstly, let's begin with the term precision. It has two forms, the first of which is instrumental precision. Essentially, it describes how precise a measuring tool that you are using is, where the smaller the measuring divisions, the more precise the measurement. We can see here on the right that ruler B is more precise than ruler A due to how it has smaller measuring divisions. And in line with what we have learned in lesson 1.1, it can record measurements to an additional significant digit than that of ruler A. Now, data precision, on the other hand, refers to how close data values are to one another, or, in other words, consistency. Really, it just means how true the data is to itself. Data precision is measured with something called percent difference, which we will cover later in this lesson. These two tables on the right, Table A and Table B, will be relevant in the next slide. Now, let's determine which data set is more precise. Without doing any sort of calculation, we can see visually that the values of table A do not deviate much. Rather, they are in a short range from 2.48 to 2.51. Table B, on the other hand, has a wide variety of values, ranging from as low as 2.31 to 2.68. With this reasoning, and because precision is about how close measurements are to one another, we can determine that table A has the more precise data. Moving on, accuracy measures how close a measurement is compared to a true or accepted value. And it is affected by systematic errors, which are due to things such as a miscalibrated instrument, and it is measured with percent error. Both of these concepts we will get into in just a few more slides. Up to this point, you should have realized that although precision and accuracy are used interchangeably in casual, everyday conversation, they actually have fundamental differences, which we have just covered. Next, let's determine which data set is more accurate considering a true or accepted value of 2.55 meters. What we can do is take an average of the data points in table A and take an average of the data points in table B and compare them to see which is closest to the 2.55 meter true or accepted value. Firstly, I'm just going to write average. The average of the data points in table A is equal to the sum of all the data points divided by the number of data points that there are, which in this case is 4. So I'm going to say that it's the sum divided by 4. And if you add all the data points up, you should get a value of 9.98 divided by 4. And if you put that in your calculator, you get a value of 2.495. And you can do the same thing on table B, take the average. And the sum in this case is exactly 10. I'll just write this as 10.00 divided by 4. And that should get you a result of 2.50 meters. And so, since table B has an average closer to 2.55 meters, then table B is actually more accurate. This also just goes to show that high precision doesn't also correlate to high accuracy. Now, we're finally getting into those terms, percent difference and percent error, which can be used to quantify data and, in turn, errors. Percent difference measures precision, and it is calculated by subtracting the lowest value of a dataset from the highest value, and then taking the absolute value of this difference divided by the average of that dataset. With this result, multiply it by 100 to receive a percentage. Percent error measures accuracy, but as you have seen in question number 2, it requires a target value or a known accepted value to compare the data to. It is calculated by subtracting the accepted value from the measured average and then dividing this difference by the accepted value. Then you multiply the result obtained by 100 to get a percentage. Now, let's actually calculate percent error and percent difference with an example. Using percent difference and percent error, let's identify which dataset is more precise and which is more accurate. So the first step here is to calculate the average of the data values in table A and the average of the data values in table B. This can be achieved by adding all of the values divided by the number of data values that we have. So 51.8 plus 52.2 plus 52 plus 51.9 is equal to 207.9 divided by 4, which is the number of data points that we have. And in doing so, we get a result of 51.975 kilograms. Now that we have this, let's calculate the average in table B, which again follows the same steps, just with different numbers. So the sum is 48.4 plus 51.3 plus 49.7 plus 50.8. And so we get an average of 200.2 divided by 4 data points. And so we get an average mass of 50.05 kilograms. Now that we have this, let's go back to table A, and we're going to calculate the percent difference. So I'm going to abbreviate that as percent DIFF. And we will take our highest value, which is 52.2, and subtract it by the lowest value, which is 51.8. Then we will take the absolute value of this difference divided by the average, which is 51.975 kilograms, multiplied by 100. And so if you go ahead and do this in your calculator, you get a result of 0.76960%. Now let's calculate the percent error. Just going to abbreviate this as ERR. We're going to take our measured average, which is 51.975, minus the accepted or the target value of 50 kilograms, divided by the accepted value of 50 kilograms, multiplied by 100. And in doing so, you should get a value of 3.95%. Okay, now let's move on to table B. Same steps again, but just different numbers. We're going to take our highest value, which is 51.3, minus the lowest value, which is 48.4. And we're going to divide it by the average, which is 50.05, multiplied by 100. Calculating this gives you 5.794%. And of course, we have to calculate our percent error as well. So we will take our measured average, which is 50.05 minus our accepted value of 50 kilograms divided by 50 kilograms, which is also the accepted value, multiplied by 100, and we get a value of 0.100%. And so from these calculations, we can determine that since the percent difference is lower on table A, then table A has the greater precision. However, if we look and compare the percent error of table A to the percent error of table B, we see that table B has the lower percent error, so it has the greater accuracy. There are two key types of errors, which I had promised that I'd get to eventually, and they are random and systematic errors. Random errors are small, unpredictable changes between trials, usually caused by things like fluctuating environmental conditions, and they cause measurements to vary slightly around the true value. Random errors can be reduced by taking more trials and averaging the result. It's also important to note that random errors affect precision. On the other hand, systematic errors are caused by a consistent problem in an experiment, whether due to factors such as an incorrectly calibrated measuring tool. Systematic errors skew data in the same direction every trial, affecting accuracy. Next, let's identify which of the following are a systematic or a random error. Question number 1. A stopwatch is started slightly late on one trial, but slightly early on another trial. This is a random error because the timing changes unpredictably from trial to trial, so the measurements vary randomly. Number 2. A scale reads 0.3 kilograms too high before anything is placed on it. Well, the scale has a consistent offset, so every measurement will be too high by the same amount, so this is a systematic error. Question number 3. A student estimates the position of a ruler marking slightly different each time. Well, the estimate changes each trial because of human judgment, causing small, unpredictable variation. And so, number 3 is also a random error. Number 4. A thermometer is incorrectly calibrated and always reads 2 degrees too high. Well, because the thermometer is miscalibrated, all readings are going to be shifted in the same direction, so this is a systematic error. Number 5. Air currents in a room cause small changes in the flight time of a paper airplane. Well, the air currents vary between trials, causing unpredictable changes in the results, and so this is a random error. Lastly, number 6. A student drops a test tube, causing the sample to spill. Well, this is neither a systematic or a random error. It is actually a mistake or a blunder, and it is not a normal source of experimental uncertainty, which is why it does not fall under either of the two categories. Let's summarize what we have gone over in this lesson. We looked at the differences between precision and accuracy, as well as the two main types of errors, systematic and random errors. We also looked at how to quantify errors with the concepts of percent error and percent difference. In our next lesson, we'll actually be moving into our next unit, which is kinematics. And we're going to look firstly at the basics of motion, then we're going to look at scalars and vectors and what is the difference between these two, as well as distance, displacement, and total displacement. Thanks for watching. Consider leaving a like if I helped you out, and subscribe if you would like to follow along with the rest of the series.